So you may or may not have seen this topic earlier. Maybe the name is lifting the exponent lemma.
Okay.
It's a
I have
name.
heard about it.
It's a popular, but it's not difficult. So lifting the exponent lemma. So we will discuss the little bit theory here, and then you can try the problems later. I have one PDF in mind which I will share with you, and you can it's someone's, and then you can just practice from there, and we can discuss the questions next time. Anyway, so lifting the exponent lemma is what the name is. So here first, maybe some very straightforward questions. Here, let's say that, can you show, so can you show the way I should say this is, yeah, let's say that, can you show that 6 to the power 5 minus 1 is divisible by 5?
Yes.
Okay, so what's the reason?
There is one factorization where 6 raised, I don't remember that exactly, but
Okay.
For any n, a raised to power n minus 1 is divisible by a minus 1.
Yes, right. So that is a correct fact, and that will be our starting point, kind of. But then how do but we need to know the proof of that. It will be important. So
Proof can be like this, that 6 raised to power 5 minus 1, like if we write it as 6 minus 1 into 6 raised to power 4, yeah, plus 6 raised to the power 3, okay, plus so on till 1.
right.
Then
And
we
so
can supply the GP thing, that it is a GP, and we solve it to get.
yeah, you mean to prove this thing?
Yeah.
Yes, right. So that's correct. Yeah. So basically, then we will be assuming this. So this is a very simple problem. So okay, and we will be needing this factorization which you have stated. So, and since you can also prove it, there is no problem. So this will be one of the requirements.
Yes.
Right. And another one which we will need is for n equal to odd, for n odd.
For n odd, a raised to power n plus 1 can be factorized into a plus 1 into a raised to power n minus 1 minus a raised to power n minus 2 plus a raised to power n minus 3 and so on.
Right. Yes. Minus 2 plus. So using alternatively. So what should the last sign be?
It should be positive.
Yeah. Okay. Right. So these two factorizations we have. Okay. And using this, we can solve this kind of question. Okay. Now this is where we change the question. We say, okay, show this is fine, but can you show now that 5 square divides 6 to the power 5 minus 1?
Yeah. Like we can use basic modular arithmetic.
Okay.
Telling
So
that 6 is 1 mod 5. Oh, sorry, 6 is 1 mod 5 square. Sorry, it's not 1 mod 5 square. It is 6 mod 5 square. Yeah. And 6 square will become 36, which is 11 mod 5 square. Yeah. And then 6 raised to power 4 will become 11 into 11, which is 121 mod 25. So that comes out to be 21 mod 25.
Right.
Yeah. And 6 raised to power 5 will become 21 into 6, which is 126, 1 mod 25.
Right. So it is indeed correct.
Yes.
Right. So certainly this is one way, but can there be a better way to do this? That is the question. Like something that does not rely on, because you see, like if we made this 5 cube, then how would we know? Then the checking would become more and more difficult. So
Yes, sir.
so think about it for a minute. What can we do to do this in a different way?
Okay.
This is just a general. Like, for example, my claim is that even if we put like, well, yeah, the proof will be equally simple. Like this would also be divisible by. On the other hand, you can see that, for example, 5 square does not divide 16 to the power 6 minus 1. Okay, this I'm not asking you to show, you can just check it. Does not divide, sorry.
Or
And
is there like any pattern, because you wrote first 6 raised to power 5 minus 1 and now 16 raised to power 5 minus 1?
Yes, there is a pattern, and that pattern is doesn't just have to do with these things in the base, but it is also has to do with this power, which is 5.
Yeah, power only I'm talking, because the power is same in both the things you gave. I
Huh.
think that we can show it by binomial theorem, like, because if we have, let's say, like 16 raised to power 5, we can write it as 15 plus 1 raised to the power 5 minus 1.
Mm-hmm.
Then we can expand it by binomial theorem, and the 1 will get cancelled, and we'll in the end we'll have something like 15 into 15c1 15c4, yeah, 15 into 15, which is 5 square divisible by 5 square.
Right, that is correct. Yeah, this 5 and this 15 both will give you 5s. That's correct. Yeah. So then, okay, then let us see if you can use that method to go further. So yeah, let's see. So suppose that x is congruent to 1 mod p. Yeah. Then can we show that p square divides x to the power p minus 1? You see, this is a similar kind of question. Yeah?
Yes, sir. That means that x is of the form pk plus 1.
Mm-hmm.
Like if,
Right.
yeah, and using the same, like I told binomial theorem, so pk plus 1 raised to the power p minus 1.
Yes, I
Yeah,
think it will work. Yeah, using again
yeah,
binomial expansion.
1 will get cancelled, and in the last it will be pk into pkc1, something like that.
PC1, right? Something, yeah. Right, and which is divisible by p square, and the other terms are also divisible by p square. So it's correct. Okay, right. That's perfect. So we have proved this. So now, so this is where the lifting word is there, right? We always knew that p divides this, because p divides x minus 1, in fact. That even happens at the level of polynomials. But now we are learning something more. This is the lifting, which we are able to lift the power to square, and we're able to comment if it's divisible or not.
Yes.
Okay. So now the question is that, can you show that p square does not divide x to the k minus 1 if k does not divide p? Or maybe this is wrong. I meant to say p does not divide. All this condition is still there.
Okay, one more time we apply binomial theorem on this only.
Right.
Pk plus 1 raised to power k. In the last, the only difference will be that it will be pk into kc1. So so it will become pk square, which is not divisible by p square.
Right. That's not divisible by p square. Perfect. And the other terms are divisible by p square. That needs to be just said, right?
Yes, sir.
Yes. So that is obvious, and so that's So then this is also we have proved. So now we can collect all these results, and we can see what we have proved finally. Yeah. So we have shown that the largest power of p. So I'll start using this notation. Okay. This is VP. This is just a notation to conveniently write something. It's not a new idea or anything. That VP of any number, maybe in this case, VP of, wait, do I want to say number or not? Yeah, we can say VP of M is equal to, is by definition, it is the largest power of P in M. This is just a notation, okay? So with this notation, what have we learned? We have learned that the largest power of P in x to the power P minus 1 is equal to 2, provided x is 1 mod P.
Yes, sir. Okay.
So we have a very exact result, that it is divisible by p square and not by p cube. Okay, yeah, sorry. I think we have not proved it, right? So you need to show that it is not divisible by p cube. So or is it correct, or is this wrong? Yeah. So yeah, let us just check that. So what about this?
It will not be divisible because in the last again the term will be pk into pc1, so it is p square k. The last term will be p square k, which is not divisible by p cube, and other terms are divisible by p cube.
Yes, but we don't know about k, right? We don't know anything about k.
And we know that p does not divide k.
No, we don't know that. Sorry. So this was a different. This was a different version. Okay, I think we have two k's going around, so that's a confusion. So just remove this. Yeah. Now we don't know that so this k is our x equal to pk plus 1.
Yes, sir.
So now we don't know, right, if p divides k or not. P can divide k, right? So it can actually.
We can make two cases, right? If p divides k and p does not divide k.
So if p divides k, then what?
If p divides k, then p cube is divisible by the last term. Like
Yes,
that, then p cube divides x raised to power p minus 1.
that's right. Yeah. So if maybe if p divides k. And if and only if you can already can see, if P doesn't divide K, then it is not.
Yes, son.
Yeah, P doesn't divide K, then basically, or from what you have said so far, then P cube does not divide. So, okay, so then what have we learned so far, right? We are seeing that this basically we are seeing that the power of P that divides this expression, right? Hold on, wait. Yes, right. So the power of P that is dividing this expression is it seems to be dependent on two things, right? The power of P, so this thing, right? This thing, or maybe write it differently. The power of P that divides x to the P minus 1, it seems to depend on the power of P that divides x minus 1, right? It depends on
Yes,
this. And obviously there is this P here, so it depends on that as well, right?
yes,
Okay,
son.
so one second. Yeah, so now maybe we can, in order to make this thing precise, we want to just, yeah, let us try to prove this result and to make this. Basically, we will show that, we want to show that this is equal to this plus 1. See, that has been the pattern. Right? The power of
Yes,
P that divides x minus 1 plus this power of P that is here, which is just 1. Okay. So in order to show this, we want to look at this simpler. It is simpler in one sense, but not simpler in other sense. Maybe let us see. So what we would like to show is the for now I want to go beyond my x1 and make it a y. Okay, so let's say that x is congruent to y mod. Should I keep it p or yeah p? So let's say x is congruent to y mod p. Okay, and let us say that p does not divide n. Okay, then we want to say that the power of P that is in this. So this just reads as highest power of P in x to the power n minus y to the power n is in fact now equal to the highest power of P in x minus y. Okay, so this may not be completely trivial, but we will prove this. Okay, but before you start to think about this, I just want to say that we have sort of already seen this kind of pattern, right? So we saw that like 5 was dividing 6 to the power 6 minus 1, but 5 square was not dividing, right? So it all had to do with the power of P that divides 6 minus 1. So that is what is happening here. Okay.
yes,
Yeah.
son.
So try to prove that this will be our starting point. Then later on we will say that, okay, if P and N, if then we will say that, okay, if VPN is equal to R, right? If P to the power R divides N, then this will also come in. But right now that is 0 because P does not divide N. Okay.
Okay.
So that we will show later, but first we will do stepwise easily, slightly. Yeah. So to give this a try and see. And maybe I'll just interrupt and add that P does not divide X and P does not divide Y. Okay. This case we are removing. So in a way, you see, this is like a simple case. This will be like, this will not add any new information. Why? Because if P divides X, okay, and P, so if, so let's just think about this. If P divides X, because you may think, why is this new condition coming? It's because if P divides X, and we already know that P divides X minus Y, that implies that
Then P divides Y.
P divides Y. But then what happens is you can take the power, you can take that P common from X and Y, right?
Yes.
You can write like this, and then what happens? Then it is like this, and then this P to the n you can forget, right? And again you're back to the same kind of problem where P doesn't divide, at least one of them, and hence both of them,
Okay.
right?
Yes.
Because if you can again keep taking out the power of P, right, till you get to the point where P doesn't divide one, and hence it doesn't divide the other. Otherwise P will not divide X minus Y, then that's also uninteresting. So this is an uninteresting case, so we kind of pull out the powers and we say P doesn't divide X and Y. Okay.
Yes.
So
Oh,
that's just a simplification. It's not meant to complicate the problem. Can we try using binomial theorem again? Are you doing that?
no, I was like x raised to power n minus. I first said that let a be the largest power of p in xy.
Hmm.
Then we can write uh, x minus y as p raised to power a into b.
Hmm.
Right, p raised to power a into b. Yeah, and now we 3 of p and yeah, and now we can write x raised to power n into y minus y raised to power n
Hmm.
as x raised to power n minus 1 minus y raised to power n minus 1.
Okay, right. Like this. Okay.
Yes. And maybe then we could expand and see something. I was just trying in that way. I don't know
But how will you
whether it
expand
will
from here?
expand in the sense that in the starting you had given one formula, right? X raised to power n minus 1 is
Uh-huh.
x minus 1 into
Yes,
x
yes.
raised to power n minus 1, like
Right,
that
right.
way.
Yeah, I think you're on the correct track. You should try to apply that. You can try to apply that formula. Yeah. Try for a few minutes, then we will.
Okay, fine.
That might. Anything?
No, sir,
No.
I'm not
Okay.
able to.
No, I think that your good binomial method will work. The same binomial theorem will work. The same thing that you are doing so far will work. You don't need this factorization even. So it's very strange. It's very nice because if you see the proofs in the books, or they actually use this factorization which you were trying but not getting. Okay. But in fact,
Yes.
from your method of binomial theorem, which I was not using earlier, okay, it actually works. Okay, just use the binomial theorem. So the hint is to just use the binomial theorem. Just try it once. Just use the same thing which you have been doing. So like, see, what you were doing is, so we had this thing. So earlier we had x to the n minus 1, right? And you were using the form of x, right? I mean, now again, you can just use it, right? So you can use it like this. And now you can do the expansion.
Oh,
Yeah,
yes, sir.
and even if you like, even if you do it in your own way, like even if you just do that x minus y is pk, it will still work, right? X equals to pk plus y. Even if you just do this, right? If you just put x equal to pk plus y in this and expand, it comes down to the same thing, and it will work. But let's just see it in action quickly, because this is just a theorem that we are proving. So but it's very important to be able to prove these things on your own. That will help you to, so that will always make you comfortable with the result, that you'll be confident, okay, I remember it. Or even if I forget it slightly, I can quickly work it out. Okay, so you don't have to, it won't feel like a baggage, because soon you'll be learning a lot of theorems. So anyways, let's move to the matter. Yeah, so it's again the good old expansion, and yeah, it's very amazing how powerful the binomial theorem is.
Yes, sir.
Yeah, like we think, oh, it's the same thing, but it's somehow it seems to give a lot of results. Yes, so why no, so this is n minus 2, or does it? Let us see. Usually the proof is using some congruence and modular arithmetic and all, but it just works like this, I think. So it's n minus 1 plus y to the n minus y to the n. Now, see, now I will want you to be able to conclude from here. Let us see.
The last term, which is nc1 into x minus 1 into y raised to power n minus 1.
X minus y.
Over here, yeah, x minus y, yeah. So over here, we have x minus y has some power of p, like a, the greatest power of p, that is a, yeah. And y raised to power n minus 1 is no, p does not divide y, so that has no power of p. And n, p also does not divide n, so that also does not have any power of p. So the greatest power in this whole expression will be p a, like of p will be a only.
Right. Okay. Okay. So here we are learning that this is just a, and so what? But why can't a greater power divide the whole expression?
Because it will, if we have, like, say a plus 1 is the greater power, then it may divide the other terms, but not this term in the expression.
Yes, it will divide the other terms.
Yeah, it will divide the other terms, but maybe not this term in
No,
the, it will
definitely
not
not.
divide. Yeah, not maybe, it will not divide this term.
And hence it cannot divide the sum. Right. So
Yes.
that is just important to write for the sake of writing the argument, at least. Like, you know it, but you have to just write it. Okay. So what we are using is that, let if some, maybe some m divides a plus b, and m does not divide a. Sorry. Yeah. So if m does not divide a, but m divides b, that implies m cannot divide a plus b. This kind of thing you are using. Okay.
Yes.
Maybe this A and that A is different, but you can understand this R and S. Yeah. Okay. This is the kind of thing which you have to use to conclude. Okay, then we are done. Right. This is the thing. So we have our, this is like our starting point. This is a zero case. This is a zero case when P has nothing in N. And then we will make it precise. We'll try to make it precise. Let's see how much, if we can do. Otherwise, we'll look at the book a little bit. But let's see, hopefully we can do it. No, in fact, this is not in that book. It is in that PDF. So I'll share with you and you can try problems from there after the class. Okay, so so we have proved this. Yeah, this also we don't need now. This also we don't need now. Right. Okay. Now we will want to. Yeah, of course we want to. So what we have proved is this, that if VPN is 0, then this is equal to this, right? Plus VPN. And we want to now, as you can expect, it is to go here. Right? Yeah. So try it as usual. I'll just say try it and see.
Okay.
But notice one thing, that this p because this may it may be a trap in applications, that you should know that p divides x minus y or p divides x minus 1. This thing is needed. Like this thing cannot be 0. We were using that in the
Yeah.
result also. Okay, so
Yes.
that is important. Otherwise, this result does not imply that does not apply. Okay.
Okay.
P has to
Okay.
divide that x minus y. It may not divide n, but p has to divide x minus y. Okay.
Okay. Okay.
Yeah.
So like all of the things that we have discussed till now, for that P needs to divide x minus 1.
Yes, like even we started with p dividing x minus 1, that thing. So the starting point was also like that. So yeah, that is necessary.
Okay. I think I have proved it.
Okay.
Similar way only like how we did it last time. First we expand by binomial, and yeah, then only we are done. And let's say that one more thing, that let's say the highest power of P in N, that means VPN is C.
Okay.
Yeah, and the previous one is same, like it's A. VP x minus y is A.
Okay. The same expansion we will do.
Yeah.
Okay. Then
X minus y raised to power n plus so on till NCN minus. Okay. Same thing. NC1. Same.
Okay. So okay, let me write the last two terms and see. So this will be square. Okay, then how do you reason?
Yes, sir. Then we have x minus y is p raised to power a into b, because that's what we have given. And yeah, and we have n is equal to p raised to power c into d. Here we have NC1, so it is n. Like Yeah, into y raised to power n, and y has no power of p because it does not, because p does not divide y.
Yeah,
So
so
this becomes p of a plus c into b d, and where p also does not divide b and d,
yes, that is okay.
because
Yeah, that is fine. So p divides a plus c, but in this case, but now the other terms, it can become interesting, right? What means, like, so you
but
have to,
if let's say that some higher power divides the other terms, then it
okay,
will not divide this term.
but does it divide the other terms? So that's the thing. In this case, now it becomes different, right? Or am I incorrect?
It will always divide, because always n divides uh nc, like
No,
nc1 nc2, it
no,
does,
it
I
doesn't
think.
divide NC2. Does it divide NC2? Why?
Yeah,
No.
nc2 is,
Okay,
wait,
let's see. And it, no, it doesn't happen.
it does
It's,
divide.
no, okay. Does 3 divide 3C2? Or 3 will divide, but okay, let's see. Does 4 divide 4C2? No. It does not
No.
divide. This is, it becomes slightly interesting now. It's not the same thing.
Yes.
Yes. So, okay, so only 1 minute is left. So just join again and we'll try to continue this. Okay. Yeah. It's there is something to be done here now. Slight change. Okay, let's see.